Actually. Hello everyone. Welcome to the very first meeting of the Conversational AI Reading Group. We plan to have it every Thursday, and we're going to talk about recent advancements about conversational AI, speech processing, and anything related to that, the multimodal foundational model, EEG data. And we have lots of speakers from academia, from industry, and looking forward to seeing you in the following meetings. For more information, please scan the code and visit more information at our website. So for today, we have the pleasure of having Peter Plantinga from McGill University. So Peter is a postdoctoral researcher at McGill. His research, he has published extensively on enhancing the speech intelligibility in noisy environment for both human listener and automated system. He is a core developer of the open source speech brain toolkit and previously led a speech AI project at JP Morgan Chase Machine Learning Center of Excellence and contributing to several patents in conversational AI technology. Peter's current work sit at intersection of neuroscience and AI, aiming to develop the understanding and treatment of different neurological disorders. Please welcome Peter to the stage.
Thank you, Bruna, for the kind introduction, and I feel very honored to be the first guest here at the Conversational AI Reading Group. So today, I want to talk about some work I did at JP Morgan Chase that I'm very proud of, that is being published in about 1 month at SLT 2024 in I think. So yeah, I did this work with some of my teammates at JP Morgan in the Machine Learning Center of Excellence, where I got to work on problems that were a nice fusion of practical business problems and research doing things that people had not done before. So I feel lucky that I got to work for that organization, and I want to also thank my co-authors, Jaquan, Abednego, and Chandra. They also deserve a lot of the credit for this work that I'm presenting today. So the topic today is continual learning for end-to-end ASR. Basic idea is when we take a large pre-trained model like Whisper or Parakeet. Nemo has several like Parakeet and Canary. If we take those and fine-tune them for a specific use case, how do we prevent the phenomenon known as catastrophic forgetting? There's a number of strategies that have been used in the literature. I'll go over a couple and then our proposed solution. So one is replay. In this scenario, basically, you take data from the original training domain and review it while you're training on new data. Unfortunately, for large pre-trained models, the data is often not available. Another technique is freezing parameters. There's a recent paper by Shinji Watanabe and his group about training only the encoder. Leads to no catastrophic forgetting, but they unfortunately are not able to mesh full fine-tuning performance. Loss regularization techniques, like learning without forgetting, still sometimes results in forgetting, ironically, and adapters are also designed for this problem, but they take a slightly different formula where instead of saying we want one model that's good for all the domains. The adapter says, let's make small models or small adaptations to models for all of the different domains. So inference time, you need to know what domain your input came from so that you can swap your adapter to be the correct one that was trained on that domain. So that's one limitation of adapters, is you have to maintain different models and know which one you need to use for a given input sample. So our proposed solution is called average of domain expert. We train, instead of training in sequence on multiple domains, we train in parallel on the domain and then merge the resulting models. This results in one model that does well on all the domains and has very, very little forgetting. So here's the diagram that sort of demonstrates.
We talked a little bit closer to the microphone that the online participant would not hear about.
Okay.
Closer to the microphone.
All right. So this diagram shows basically the setup that I have, the paradigm that we're proposing. So the traditional continual learning paradigm is training one model on several domains in sequence, trying to reduce forgetting at each step as much as possible. But for the average of domain experts, we proposed training in from the same starting point on several domains, and then we're averaging or merging the resulting model into a single model that performs well on all the domains, and we're much less forgetting. So each of the experts might have a significant forgetting, but once you do the merge, it has a lot less forgetting. And you can do this multiple times. You can train on several domains and then average, and then train on more domains and then average again. So the idea of model merging or model averaging is not a new one, but I think that it has been overlooked for the problem of continual learning. So in federated learning, where you have cases where some data is private, you don't want to share the data, you can train a model on your private data and then share the model and average the model with other models trained on private data. For improving generalization, so stochastic weight averaging is a pretty famous paper, and they take several checkpoints along the training trajectory and average, and in this they find improved generalization. For distillation, there's a paper that shows that the average of several teachers can actually provide better guidance to a student model than just a single teacher model. And then of course, the elephant in the room is LLMs. The field is kind of exploding, merging LLM models. So training Llama on a specific subdomain, several, and then merging LLMs. I mentioned 4 different papers here, different techniques for model merging, but there's hundreds of papers on this now, and it's only growing. This figure is from a sort of review paper of model merging in LLMs, and they sort of show 3 different paradigms. We have the separate model paradigm where every model is trained on its own data. We have ensemble learning paradigm where models are trained and then their outputs are merged. And then we have the model merging paradigm where not just the output, but the entire model is combined into one single model that performs on all domains. So it's relatively newly popular in LLMs. I mean, LLMs themselves are new, but it's getting a lot of popularity there. But yeah, the main point of this slide is this is not a new technique, but it's not often been applied to continual learning, and I think it sort of deserves more attention for that problem. So for our baseline for our main comparison method, we experiment with layer-wise learning rate decay. This technique takes each layer and applies a different learning rate, highest learning rate for the topmost layers. I don't think this technique was specifically designed for continual learning, but it, in our experiment, showed very similar or better performance than the most popular continual learning techniques. So learning without forgetting, training only the encoder and not the decoder. These are, popular papers, and we get better performance using layer-wise learning rate decay. So this chart, so the graph shows basically what I'm saying. We have warm up and cool down, but at every step, every lower layer has a lower learning rate than a higher layer. And you sort of apply a factor of, say, 0.9 to every successive layer under the topmost layer. So applying this technique, we improve actually both the final performance and the forgetting rate, which is a nice indication that it's working, right? So alpha 1.0 means all the layers have the same learning rate, and then 0.9 means every layer has 9/10 the learning rate of the layer above it. And using that technique, we go from 14% to 12% in word error rate, and forgetting rate goes from 60% to 20%. So it's improved on both the word error rate and forgetting rate. And then if you go even further, you can reduce the forgetting at the cost of a higher word error rate. So alpha is 0.8, we get 13% word error rate and 7% forgetting rate. So I should note that the metric we use for forgetting here is increase in performance on liver speech, and clean, and other. So basically, the pre-trained model has, I don't know, this is Whisper, so I think it's like 2.5% on word error rate on text clean. But as you train on other domains, in this case, the Corral data set, the performance on liver speech gets worse, and we measure the percent increase in performance on liver speech as our measure of forgetting. Another technique that, again, maybe wasn't designed for continual learning, but actually does seem to work for continual learning, is LoRa itself. So this figure is from the original LoRa paper. You add additional smaller weight matrices alongside the frozen original weights, and the idea is that if you know that your sample is from a new domain that you trained on, you can apply these additional weights. But if it's from the original domain, you don't need to apply the weights. But we find that it does actually help with forgetting in a similar way as learning rate decay. So applying LoRa, we get less forgetting from 120% to 88%. at the cost of a slight drop in performance. So that's sort of an interesting result. So I'm going to go into a bunch of the experiments that we did. I want to apologize in advance. There's a lot of results tables, but I tried to pick out a few interesting notes about every single one. So I hope you learned something from everyone about the phenomenon of forgetting. So here we have two generalized models. We have minimal parity. Most of our results are from this. We also have some results from which were small, and they were both, large transformer-based models, trained on a lot of data, although they do have different training schemes. One is CTC and one is autoregressive encoder-decoder. So they have different loss functions, which increases the generalizability of our results a little bit. But the main thing is we had a lot of different data sets. So they cover many different sizes, 5,000 hours down to 1 hour. We have many different domains, news, finance, everyday conversations, and many different conditions. We have, the finance, speech is like earnings calls where companies are talking about the last quarter or whatever, and they have a large vocabulary of finance-specific terms. We have dialects, we have added noise, we have conversational speech, emotional speech. So we're not just training on a few data sets. We're not just training on a few data sets that are similar and then averaging the results. We're training on different data sets and then averaging the domain experts. So I'm going to go through a number of scenarios that roughly correspond with different use cases or different assumptions that you make about the data in order of complexity, roughly. So the simplest scenario is straight fine tuning. Everyone, I'm sure, is familiar with this. So sometimes just fine tuning on your data set gives you the best performance. And if you don't care about other data sets, then this is fine, right? I just want the absolute best performance on my little finance data set, and I know all of my inference samples are going to come from this domain. I don't care about getting. This is sort of the scenario I'm going for here. So in this scenario, I'm going to spend some time on this result table because there's others that are kind of like it. So we have all of our test data sets across the top, noisy, VCTK, we have Corel, we have DL Corpus, Google Any, and then Liver Speech, Test Clean, and Test Other. We don't ever train on liver speech. This is just a measure of how much is it forgetting on these data sets. And then average column is average performance across all of these other data sets. And then the forgetting column is percent increase in performance on liver speech. So as you would expect, fine tuning on each data set leads to the best performance on that data set. Which you can see from the diagonal across the table, where fine-tuned on VCTK has the best performance on VCTK. So we have in the forgetting column, all of these lead to pretty big forgetting. Yeah.
Just explain what the forget metric is. Is it bigger the metric? What is the definition of the forget percentage here?
Yeah, so if you look at the first and second row, the first row is a pre-trained model, which gets an average of 3% roughly on litter speech text data set, if you average the two columns. And the BCTK is more like 6%. So, take litter speech testing and test other, average those two columns, and then how much higher is, how much worse is the performance after fine tuning. So let's say JL corpus here, we're getting 13% on test other and 7% on test clean. That's roughly 260% of the word error rate of the pre-trained model, which is 4 and 2. Does that make sense?
Yes, but what is that metric? 2.0, 3.7. What are these the word error rates?
These are word error rates. Yeah, this is word error rate.
I see. So the baseline is set at pre-trained, and then compared to that, how much worse was it?
Yeah.
Thank you.
Any other questions about the data in the table? So, yeah, like I said, JL corpus has the word forgetting, and this is even JL corpus is also the smaller data set, which might not be what you expected. So it's only 1 hour of data, but it still led to the highest rate of forgetting. And our observation was that data, it wasn't necessarily related to the size of the data set or the number of updates, but rather how narrowly or cleanly distributed the data was. So JL corpus is a bunch of voice actors all saying the same phrase in different voices. So it's possible for the model in some cases to memorize what the phrases are, and that's sort of like how shows you how clean or narrow the data set is. Another note is, as expected, the average performance across all data sets is the best for the pre-trained model. All the other ones reduce their performance when you look at all of the data sets combined. So our second scenario here is if you have a short retention period, your data is only available for 30 days, or for privacy concerns like federated learning, you may not have available. Some data may only be available to some people and not to others. So to simulate this, we sort of never show the model a data from more than one data set at a time. So, yeah. In this scenario, we have 3 different models here. We have the pre-trained model, we have sequentially trained model on one data set at a time in 2 different directions, and we have our proposed model that averages different experts. As you might expect, the sequential training tends to do better on more recent data sets, although not always. And that's, might be the desired behavior in some cases. But in either case, the forgetting rate is quite high, 140%, whereas average experts is, between 4 and 9%. And the difference between the two average of domain experts here is that in one, we just averaged our 4 domain experts. And then in the second one, we actually include the original pre-trained model in the average. And that gives us five other models that are in the average. And that reduces the forgetting by about half, from 9% to 4%. One interesting note about this last model is that we actually see an improvement on liver speech test to clean, even though we've never shown the model any data from liver speech. So it's only trained on BCP. You know, we have our core model trained on BCPK, Corral, JL corpus, Google NE, which are all domains that are quite different from liver speech. But when you average them along with the original model, it's actually performing better on liver speech test clean than the original pre-trained model. So that's kind of an interesting, a cool little note. Yeah.
So for the average column, that's the average between test clean and test other.
So
The average column, the second last column, average.
yeah.
What is the average of? It's the average of test clean and test other.
It's the average performance across all of the data sets. Yeah. So it's just to give you a sense of how generalizable is this model. Does it generalize to many different types of data? So yeah, averaging the 4 sets gives you the best average performance across all the data sets. The second part of this scenario, we wanted to compare averages between experts, both with and without using LoRa. So LoRa, as I said before, can be seen as a technique to reduce forgetting, even though that's not sort of its intended purpose. So we wanted to compare average of domain expert of fully fine-tuned models as well as LoRa, which might reduce your training costs as well as other things. So in order to do this, we actually merged the LoRa weights back into the model. There's this function in the efficient fine-tuning library called merge and unload, which sort of adds the weights back into the original model weights. And then you can K on the average as before. So for this scenario, we found that the forgetting rate was not really that much better using LoRa and average domain expert as opposed to just fine tuning and using the average, whereas the average performance or the generalized performance was actually worse. So after this point, we don't really show many more experiments with LoRa because of this result. We ran more experiments, but they show the same thing where we're getting it basically the same, but the performance is a bit worse. All right, so now we get to some more interesting scenarios. We have this scenario where all of the training data is available all of the time. So you can do whatever you want, like you can combine all of your data sets, you can resample the data sets, you can, and then for the average domain experts, what you can do is you can actually iteratively train and average and train and average, where you take the average model and further fine tune it on the same data set, and then average again, and this improves the performance to some degree. Any questions about how the iterative training scheme works?
A couple of questions in the online meeting, but we will ask them at the end.
Okay. So for this scenario where we have all of our data available, we show 2 rows at the top here, combined data set, and then resampled combined data set where we sample the worst performing data sets at a higher rate. And we compare that against our average of domain experts. And As expected, average domain experts performed had a much less forgetting, but perhaps unexpected is average domain experts is actually performing better across the board. Include if you look at the average performance column, we get like 5% whatever rate on average across the board, even compared to the 6% that we said on data set. So, and then another note here is doing multiple iterations does not lead to much more forgetting. So iterating one time with 90% from the last slide, 2 times is 10%, 3 times is 12%. So that's only 1 or 2% more forgetting each iteration, but we actually get better overall performance. And then adding, one last note is for very narrow domains like this general corpus, you can actually still get better performance using fine tuning directly on that data or even including other data as compared to average domain experts. So if you all you care about is your one domain, very narrow domain like JL corpus, maybe average domain expert is not the right technique. And the second part of this scenario is you can control the expertise that you have in a specific domain by putting more weight on that particular expert when you're doing the average. So for our experiments, we have 5 component models, 4 experts and 1 original model, and we increased the weight of each of them in turn by from 1 to 4, so that it makes up half of the total weight. So half is 1 model, and then the other half is the 4 other models. So this is another result table. I would say, of course, reading one specific model 4 times compared to the others leads to better performance on that domain as expected. At the cost of sometimes this will increase the forgetting rate from 5% to 12 or 15%. But if you care a lot about one specific domain, this may be a trade-off you're willing to go with. And then one really interesting result is the very last row where we weight the original model times 4 compared to the other model, and we reduce forgetting to our lowest rate to just 0.4%, which is almost no forgetting. And sort of foreshadowing scenario 4, you could dynamically apply this. Like if you know what your incoming sample domain is, you could load up your weighted model towards one specific scenario. So our 4th scenario is Oracle domain test, but I called it basically for some of our use cases, we may know at the test time or inference time what the use case of the domain is. So this example shows for the system called IVR, interactive voice response, that will direct call based on the needs of the caller. I'm sure you've all experienced this as a computerized system on a telephone that says, press 1 for this particular use case. So for a use case like this, you can either preload or swap in the model that you want for that particular domain, which is cheaper to do for adapters than for full fine-tuned models. So for this use case, The first two models are one single model across the whole, just sort of to provide a baseline. And then the last three models, which I labeled hot swap, are ones where you swap out the model based on the use case. And you can see that average domain expert is getting a better across the board performance in both the hot swap scenario and then also slightly better performance across the board, even in the scenario where it's the same model on every single use case. There is a caveat here that average domain expert hot swap is actually more costly, it can take up more space, and it's harder to implement than using LoRa hot swap. All right, so that's all the result tables that I have for you. Thank you for playing with me through many results, and yeah, thanks again for inviting me to be the first speaker here at the Reading AI Group, Conversational AI Group.
I think there are questions online.
Yeah, because there's lots of tables, so we want to experiment with it.
Yeah, we're sorry. I think the quality of the audio wasn't really well. Can you guys confirm online if the audio is better now?
Yeah, much better with you speaking.
Okay. Okay, it's better now. Yeah. Yeah, sorry again. We'll fix that next time. So there are questions online. The first question was related to the data set. So someone asked, what if we combine all 4 data sets and then fine tune after shuffling it? Maybe that was related to the first scenario. I think that was a question that was asked at that time.
Question about combining all the data sets.
Yeah. So what if we combine all 4 data sets and then fine tune after shuffling it?
So this scenario 3A, the first 2 results are where we combine all of the different data sets, including one row where it's just a straight combination, and the second row where we resample from the different data sets based on what has been performing the worst. And yeah, as you can see, yeah, there's still much more forgetting, and the average performance is not quite as good as the average domain experts. Does that answer the question?
Yeah. So if you guys want to ask a question, maybe you can just raise your hand and I'll turn on your mic. Someone asked, better than combine. Better than. Okay. Better than combining all 4 data sets, what if we ensure that each batch contains equal proportion from each fine-tuning data or domain training example?
We did not run an experiment where every batch contained at least the same proportion of every data set. But I think the resample data set did get much better performance than the combined data set. But we were doing it more based on the overall trend of which data set is performing better or worse than expected.
Another question is, can you please explain one more time how forget metric is defined?
Yeah, so the forget metric is, let's take our performance on liver speech test clean and test other combined. So combine all the samples from liver speech test clean and test other into one set, and then measure performance before and after fine tuning. So let's say the pre-trained model gets about 3% on the combined data set, and our average of domain experts gets about 3.5%. That's going to be, I don't know, 20% forgetting rate, something like that. It's how much worse did the model perform in terms of word error rate on the combined liver speech data set. I hope that was clear.
So when you say average of domains, like, do you just simply take an average of all the model weights, or is there something else?
That's it. Yeah, it's just merging the models by taking every single weight in the same position and getting a linear interpolation. But it's a very simple technique, widely used, but I don't think it's been used for continual in this way.
Did you average only the fine-tuned models or also the original one?
So we experiment with both, including the original model reduces the forgetting. So if you look at this slide, the last two rows are the same, but the last row includes the original, the second to last does not. So go from about 12% to 5% forgetting, and similar performance across the board.
So it's like an ensemble kind of a thing. Like, has other things been explored in this area about like assigning different weights to these different learners, these ensemble, or like combining them in different ways, like bagging, boosting, something of those kind? Has that been explored?
Weighting the different components.
Weighting the different components, or like making them more sequential, saying that you train one and then you figure out which domains were harder, and then you retrain another one, do some kind of boosting.
Oh yeah, yeah. We didn't explore that at all, but that could be an interesting approach.
Developing the last line of the table. What happens if you give more weight to the original model when you combine?
Yeah, if you give more weight to the original model, you can reduce the forgetting to almost nothing. So this is the last row here. We weight the original model 4 times compared to all the other models, so that it comprises half of the total weight. So if you say 5 models and then weight one of them times 4, you get 8 total, and half of it is one of the models. We're getting down to 0.4%.
But it comes at the cost of word error rates for the domains on which you train them.
Yeah.
And that's the highest for GL versus.
I have a question. So what if the data set doesn't include a lot of training samples? Or let's say if the data set is imbalanced, how will the performance change?
So we saw in our experiments that the size of the data set didn't matter too much, but so JL corporate, you might expect that the bigger data set would cause more forgetting because there's more updates, more chance to run away from the original model, but that's not the case. JL corpus is our smallest data set, only 1 hour, but it caused the most forgetting. And our guess is that it's the narrowest, it's the cleanest data set that has like one specific purpose, which is to test for different emotional. So it's the same couple of people that are all saying the same things in different tone of voice.
Also, your forgetting is based on Libri speech. Like, could it be a property of Libri speech itself, in some sense? Like, are there other data sets that you could that you clarified that this is the behavior of forgetting on some other data set also?
Yeah, we could have checked like common voice or some other, big data set to see if the behavior was the same.
But you don't think there's anything specifically about Libri speech?
I don't see any reason why it would be different.
So basically what you explore here is mostly related to domain incremental. We try different domain data set from different domain. Have you explored like what happens if we have a task incremental, like if, for example, different language with different recognizer, if we want to add that, how in this model they could work if there's like different like expanding tokens?
That's a good question. Different. I think it could be interesting to expand this work to different languages or different tasks, where not only the domain is different, but even the output is different. I mean, there would be some things you have to figure out because you can't just average different output layers of different sizes, but I think that could be an interesting future direction.
Could you repeat why you had a slide about LoRa and you said that you won't talk about LoRa any further? Could you go to this slide, please?
Yeah, so we compare against LoRa in this table. LoRa is the third row, where we train on every data set using LoRa and then swap out the weights based on where the sample is coming from. So if we know the sample is coming from the chorale domain, we use the weights that were trained on the chorale data set to get the best possible performance using LoRa. And that's sort of what the intended use of LoRa is, that you have very cheap, small weights that you can swap out or swap in whenever you want, basically.
What happens when you average LoRa weights for different domains?
Yeah. What we found with averaging LoRa is that it didn't really improve on the forgetting. It had slightly worse performance overall, and it had about the same forgetting rate as the averaging the fine-tuned model. So,
But the error rate is lower, only 2.07 versus 2.57.
yeah,
For the core system.
VCTK and Corel are opposites, right? On one it did better, on the other it did worse. Overall, it was slightly worse.
So do you feel when you average fine-tuned models versus when you average just the LoRa adapters, averaging causes more higher error rates over the domains on which you trained with LoRa versus fine-tuned?
That's right. So, but it's not huge if you care about like the training time, it may be worth it to use LoRa here, but yeah, for the rest of our experiment, we use the fine tuning.
How big is the backbone model?
So the parakeet model is 2 billion parameters, which is, I mean, compared to LLMs, it's not big, but it's pretty big for an ASR model.
There's another question online. So someone asked, while fine-tuning models, as lower layers generally capture acoustic information and top layers / decoders are responsible for domain knowledge, any possibility of averaging only top layers can lead to better performance as compared to overall averaging?
Can I repeat the question?
Sure.
Averaging only top layer can lead to better performance. Yeah. So the question is about, could we get better performance averaging only some of the layers, only the top layers, and leaving the bottom layers as the original layers? And that's a very interesting thought. I hadn't We haven't tried anything like that, but I think it's worth checking out. Any other questions? No?
Are there any other questions online? Okay. Thank you.
For the chat. Thank you everyone who is joining. Sorry if there is some disturbance in the sound or anything. We will try to fix it for the next time. So our next meeting will be on December 5th, where Jeff Bakan is going to talk about interpretability of audio models. So we are looking forward to see you there. And thank you again for joining.
Thanks a lot.
Thank you. Bye bye.
Thank you. Bye.
Thank you.